an alpha particle, helium nucleus. So a particle has a speed that is 10% of the speed of light. So this particle has a speed which is equal 10 over 100 of c of light, of the speed of light. What is its de Broglie wavelengths in meter? And the mass of this particle is given 6.65 times 10 to the power minus 27. According to de Broglie theory, any particle of mass m and speed v, its motion can be associated to a wave where lambda of the wave is equal h over mv. This is the formula of de Broglie. Lambda equal h over mv. And pay attention, when we use this formula, all terms should be at the international system SI. The mass of the particle m should be in kilogram. The speed should be in meter per second. The Planck constant should be in joule per second. So lambda obtained in this formula is in meter. H equals 6.626 10 minus 34 divided by the mass, which is given in the international system in kilogram. We put directly the value, and the speed is given v 10% of c, so equal 10 over 100 c equals 0.1 c equals 310 to the power 7 meter per second. We put the value in the expression of lambda, so lambda obtained in this calculation is in meter. So lambda equals 3.32 times 10 minus 15 meter, and the correct answer is A. Exercise 8. Knowing the wavelengths of a photon of lambda 500 nanometer absorbed by hydrogen, move the electron from energy level 2 to 3. That means the electron is found initially at n equal 2. It absorbed radiation of wavelengths lambda 500 nanometer. So the electron will pass from the ground state or from a lower state to an excited state, which is equal n equal 3. When the electron returns from 3 to 2, it will emit radiation as light. So we have several statements A, B, C, D, and E. Which of the above statements is or are correct? A, the energy of the photon emitted by the electron when it drops from n equals 3 to n equal 2. The general concept, suppose you have electron at lower n, the atom absorbs energy, exactly the difference of energy. The electron pass from n lower to n higher by absorbing energy, which is equal to delta E, and delta E is also equal E final minus E initial, and this delta E is directly proportional to the frequency of the light emitted. So delta E absorbed equal delta E emitted equal h nu equal hc over lambda or we write it in another way, E absorbed, which is equal to the difference of energy between two levels, E absorbed equal E emitted equal h nu equal hc over lambda. We pass to the statements. The energy of the photon emitted by the electron when it drops, when it returns. Emission, return. This is true. A is correct. B, the energy of the photon absorbed by the electron. Yes. The electron could not pass from lower to higher if the energy is not absorbed by the atom or by the electron. So the energy of the photon is absorbed. This is true. I prefer to use not by the electron, is absorbed by the atom. Then energy absorbed pass to the electron. So this is the same, but I prefer to use the energy of the photon absorbed by the atom. So B is correct. C, the transition energy of the electron from n equal 2 to n equal 3, this is true. This is correct. When we pass from n lower to n higher, we called it transition. When we return from higher to lower, we prefer to use the term emission. So C is true. The part D, all the above answers are correct. So A, B, C are correct. So the answer is D. Exercise 9. What is the wavelength of a photon emitted? We can write what is the wavelength of the radiation emitted when the electron of hydrogen drops from level 5 to level 2. When the electron returns from the excited state to lower state, it will emit radiation of frequency nu. The delta E absorbed equal delta E emitted equal h nu. So we apply the formula. Electron drop from higher to lower, so emission of radiation. Here we can work on two types of calculation. We can apply Balmer-Rydberg formula for hydrogen or for hydrogen-like to calculate lambda, or we can find E5, which is equal to minus 2.18, 10 minus 18 divided by 5 squared for hydrogen, and E2, which is equal minus 2.18, 10 minus 18 divided by 2 squared. So we can calculate delta E equal E5 minus E2. So we know delta E. Then we apply delta E equal hc over lambda. Delta E is known, is calculated. H is given. C is given. So we can calculate directly lambda. This is another method. But in this exercise, since the requested is the calculation of lambda, I prefer to apply direct Balmer-Rydberg formula for hydrogen or hydrogen-like. 1 over lambda equal RH times Z square, 1 over N initial square minus 1 over N final square. So 1 over lambda, Rydberg constant is given in the exercise, 109,677 centimeter minus 1. So lambda found should be in centimeter. If RH is in meter, lambda is in meter. Z for hydrogen is equal 1 square, 1 over N initial. What was the initial state of the electron? The initial state of the electron is the N lower, is 2, 1 over 2 square minus 1 over N final, which is level 5, N5 square. So we calculated by this way lambda, and lambda is should be in centimeter, 4.34 times 10 minus 5. We transform the centimeter to meter by multiplication by 10 minus 2, so equal 4.34 times 10 minus 7 meter. The correct answer is B. Exercise 10. For which of the following transitions does the light emitted have the longest wavelengths? Pay attention that the transition is the same as the emission in the value of delta E. Delta E transition equal, يعني E absorbed equal E emitted. And always use delta E, the difference of energy between two levels, is E higher minus E lower. So what is the longest wavelengths? When the electron return from 4 to 3, when the electron return from 4 to 2, when the electron return from 4 to 1, or the electron returns from 3 to 2, or from 2 to 1. So delta E absorbed equal delta E emitted, E absorbed equal E emitted equal H nu equal Hc over lambda. And delta E equal E higher minus E lower. As lambda increase, Hc over lambda decrease, so delta E decrease. Or when the frequency, for example, decrease, delta E decrease. So as lambda increase, the mu decrease since mu equals C over lambda. The energy difference delta E decrease. He asked us to calculate or to find the longest lambda. The longest lambda, يعني the highest value of lambda. So we have to search for the lower difference delta E. Longest wavelengths, lowest frequency, and lowest energy difference. The lowest energy in general is obtained for the highest Ni and the highest Nf. Can we obtain directly the answer from 3 to 4, 2 to 4, 1 to 4? We can eliminate in the series A, B, and C. We can eliminate B and C. Why? Because in A, we have the highest and initial, and we have the same and final. So in A, B, and C, we can eliminate B and C. D and E do not have the same and initial, nor an final. So A, D, and E could not be compared directly, since we don't have common and initial or common and final. So in this exercise, the first method is to calculate lambda when the electron return from 4 to 3, and to calculate lambda when the electron returns from 3 to 2, and to calculate lambda when the electron returns from 2 to 1, then to choose what is the longest or the highest value of lambda, so you can find the answer. But if we want to do 3 calculations, it will take time. So do we have another concept of thinking? We know that we have to know that the energy levels for hydrogen are given in the following order. The greatest difference is between 1 and 2. As an increase, the difference of energies between levels decrease. So the difference between 4 and 3 is lower than the difference between 2 and 1 and is lower than the difference between 3 and 2. Look to answer A is the difference from 4 to 3. The difference from 4 to 3 is this area. Part D, the difference between 3 and 2 is this area. So the difference between 4 and 3 is lower than the difference between 3 and 2 is lower than the difference between 2 and 1. So the lowest energy difference is between n equal 4 and n equal 3, and this is the correct answer. So the answer is A. Exercise 11. Which of the following transitions for the hydrogen atom produce radiation of shortest wavelengths? This is the inverse of exercise 10. Delta E equal Hc over lambda. The shortest lambda means the highest frequency and the highest difference of energy. So as lambda decrease, mu increase, energy difference increase. The shortest lambda, the highest frequency, or the highest energy difference. We saw in the previous slide that the highest difference between levels for hydrogen atom is between level and 2. So delta E, the greatest, is between level 1 and 2. So in this case, the correct answer is E. Exercise 12. The ionization energy of the ground state of hydrogen-like species is 106.82 times 10 minus 18 joule per atom. How many protons are contained in the nucleus of this hydrogen-like? Or in other words, calculate Z of this hydrogen-like. What is the atomic number? To remember that the hydrogen-like species are systems containing one electron and several protons. When we say several protons, so A is incorrect because in A we have one proton. So the answer should be B, C, D, or E. What is the definition of the ionization energy? We said that an electron found on level n, it can pass to n higher according to Bohr theory if the atom absorbs exactly the difference between n higher and this n level. If we continue to add, or if we add greater energy, it will pass to higher level. The ionization energy, by definition, is the energy absorbed by the atom at the gas state to remove one electron from this atom. We have one electron ejected. So the ionization energy is the energy needed or absorbed by atom at the gas state to remove one electron, which is the electron ejected from the atom. Is the electron of the valence shell of the last shell of the highest N. Why? Because the electron on the valence shell is the less attracted by the nucleus, so it can be removed easily. X gas absorb energy to remove one electron, so X transformed to X plus gas plus one electron. The energy absorbed during this process is the ionization energy. So by another word, according to Bohr, the ionization energy needed to pass the electron to n equal infinity, so to outside the atom. The difference of energy, delta E, is equal to the energy absorbed, which is the ionization energy noted IE, equal E final minus E initial. According to Bohr theory, the energy of hydrogen or hydrogen-like is given by En equal minus 13.6 divided by n square times z square. When the electron is ejected outside the atom, means when the electron is at n equal infinity, so minus 13.6 times z square divided by infinity is equal to 0. So E final in this case is equal to 0. And the ionization energy is equal minus EI. What is the formula of EI? EI equal minus 13.6 z square divided by n square in electron volt. So we put the plus because we have minus before EI, or equal minus, this is a plus 2.18 times 10 minus 18 z square divided by n square. We have to correct to put the plus. Then we apply IE is given. IE is equal 106.82 times 10 minus 18 equal plus, we have to correct. I said we have to correct plus 2.18 10 minus 18 z square divided by n square. N square is the initial state, and the initial state, the most stable state, this electron is found at n equal 1. So in this case we found z square and z equal radical z square, so z equal 7, and the correct answer is E.